Bismillahir Rahmanir Rahim. I am Dr. Asad ullah, Lecturer, Institute of Numerical Sciences, Cohort University of Science and Technology. Dear students, welcome to the course of Fluid Mechanics, course code MATH-361, lecture number 13. We are in chapter number 2, Fluid Kinematics. In this lecture, we will try to cover the following points. Number 1, problems on Eulerian and Lagrangian descriptions. In the previous lecture, we theoretically investigated the relation between the Eulerian and Lagrangian descriptions. In this lecture, we will do some exercises to study the relation between the Eulerian and Lagrangian descriptions. Number 2, control volume, control surface, and infinitesimal fluid element with geometrical descriptions. We will provide the definition of control volume, control surface, and infinitesimal fluid element, and also explain its geometrical descriptions. Number 3, behavior of the fluid element in the flow field. Number 4, there will be some practice problems to the students, and finally there will be references. Problem 1. The motion of a fluid in Lagrangian system is given by equations in system number 1. Now, here x, y, and z represents the position of a fluid in Lagrangian system. Here what we have to do, we have to find the velocity components at any time t in the Eulerian system. Now in solution, differentiating equation number 1 with respect to time, we get the result in the form of equation 2. Here in system 2 we have three equations, that is u, v, and w. U is replaced with dx by dt. The velocity component v is replaced with dy by dt, and similarly the w component of velocity is replaced with dz by dt. Here y naught, z naught, and x naught is the fixed position of the fluid particle. Now to eliminate x naught, y naught, and z naught from the system of equations 2, we use the following three steps. Step number 1. Multiplying the second equation by the time t and subtracting from the first equation of the system 1, we have the result in the form of equation 3. After simplification, we get x minus yt is equal to x naught into 1 minus t cube. Dividing both sides of this equation by 1 minus t cube, we get x naught is equal to x minus yt divided by 1 minus t cube. In step 2, similarly, multiplying the third equation by the time t and subtracting from the second equation of the system 1. After simplification, we get the result in equation number 4. Here y naught is equal to y minus zt divided by 1 minus t cube. In step 3, multiplying the first equation by t and subtracting from the third equation of the system 1, we have the result in the form of equation 5. After simplification, we get z minus xt is equal to z naught 1 minus t cube, and dividing both sides by 1 minus t cube, we get z naught is equal to z minus xt divided by 1 minus t cube. Now using equations 3 to 5, in system of equation 2, we have the velocity component u is equal to y plus zt minus 2xt square divided by 1 minus t cube. Here just we have replaced the y naught value and the z naught value in the velocity component u. Similarly, the velocity component v is equal to z plus xt minus 2yt square divided by 1 minus t cube, and w is equal to x plus yt minus 2zt square divided by 1 minus t cube. These velocity components v and w are calculated in the same manner as we have calculated the velocity component u. Finally, in the form of a system, the velocity components u, v and w are given in equation number 6. Here u, v and w represents the velocity components in the form of Eulerian system, because there are no x naught, y naught and z naught, that is the fixed point in this system number 6. Problem number 2. For a two-dimensional flow, the velocity components at a point in a fluid may be expressed in Eulerian coordinates by u is equal to x plus y plus 2t and v is equal to 2y plus t. Determine the Lagrangian coordinates as a function of the initial position x naught, y naught and time t. In this problem, we are given the velocity components u and v that are given in the Eulerian system. We have to find the coordinates of the points in the Lagrangian system. In solution, the velocity components can be written as in the form of the system 1. That is, we have just replaced u with dx by dt and v with dy by dt. System of equations 1 can be written in a flatter form in the form of system 2. In system 2, the differential operator d is used, which is equal to d by dt. This differential operator d is already discussed in detail in the ordinary differential equations course. Equation 2 is the system of linear differential equations. To solve the given system, we use the famous Kramer's rule. To use the Kramer's rule, first we have to check whether the determinant of the given system is equal to 0 or not. If the determinant is equal to 0, so we cannot find the values of x and y. But in our case, the determinant is d minus 1 times d minus 2, which is not equal to 0. So we can calculate x and y. Now, in the numerator, in the determinant, the first column 2t and t, this is the right hand side of the both equations in the system 2, while the second column, it is minus 1 and d minus 2 are the coefficients of y. Now, expanding just by using the 2 cross 2 determinant rule, we get d minus 2 times 2t plus t, and similarly in denominator we get d minus 1 times d minus 2. Now, using cross multiplication, we get the second order non-homogeneous ordinary differential equations that is given in the form of the system 3. To find the solution of equation 3, there are two solutions related to the equation 3. Number 1, the complementary solution. Number 2, the particular solution. For the complementary solution, we take the homogeneous part, and for the particular solution, we take the non-homogeneous part. So, for the complementary solution, we take the homogeneous part, that is d square minus 3d plus 2 is equal to 0. Now, this is a simple polynomial of degree 2. So, using factorization, we get d minus 1 times d minus 2, which is equal to 0. And this implies that d is equal to 1 or d is equal to 2 are the two roots of this second order polynomial. Now, to find the solution, that is the complementary solution given in the form of equation number 4. In equation 4, capital A and capital V denotes the unknown constants. Here, in the exponent, before the variable t, we get the first root, that is 1, and in the second exponent, that is e power 2t, the exponent, that is 2 before the variable t, is the second root of the polynomial. Now, to find the particular solution or the particular integral of equation 3, that is the non-homogeneous part of equation number 3, we can write particular integral is equal to the non-homogeneous part, that is minus 3t plus 2, divided by the homogeneous part of the differential equation, that is d square minus 3d plus 2. Now, to find the particular solution from here, we take 2 common from this second order polynomial and use the binomial expansion. That is, after simplification, we get equation number 5. Before equation number 5, in this step, we use the binomial expansion up to first order, because second order and higher order polynomial in D will annihilate minus 3t plus 2 is equal to 0. So, as a result, we expand this polynomial up to first order, and after applying this operator on minus 3t plus 2 and simplifying this expression, we get minus 1 over 4 into 6t plus 5. To find the general solution of the given differential equation 3, we add the particular solution and complementary solution that are given equation number 4 and 5. We get a general solution given in the form of equation number 6. Similarly, to find the unknown y, we use the Kramer's rule, that is the first column is the coefficient of x and the second column is the right hand sides of both the equations. Now, using the 2 cross 2 determinant rule, we get d minus 1 times t, and in the denominator we get d minus 1 times d minus 2. So, using cross multiplication, we get d minus 2 into y is equal to t, as given in equation number 7. Equation 7 is the first order non-homogeneous ordinary differential equation. To find the complementary solution associated to the homogeneous part, this is a simple case because here d is equal to 2, so we get the complementary solution in the form of equation number 8. Now, to find the particular solution, we divide the right hand side of equation number 7 by the homogeneous part, that is d minus 2 in our case, and taking common out 2 and applying the binomial expansion, we get the result in the form of equation number 9. Now, to find the general solution for equation 7, we add the particular solution and the complementary solution that is given in equation number 8 and equation number 9. We get the general solution in the form of equation number 10. This is our complementary solution, and minus 1 over 4 times 2t plus 1 is the particular solution. Now, to find the unknown constant a and v, we will use the initial conditions, that is x is equal to x naught, y is equal to y naught, and z is equal to z naught at the time t naught is equal to 0. So, using these conditions in equation number 6 and equation number 8, we get a is equal to x naught minus y naught plus 1 and b is equal to y naught plus 1 over 4. These are the values of the constants a and b. Now, using the values of a and b in equation number 6 and 10 respectively, we get the position of the particle, that is x and y, in the Lagrangian system as described here. Now, before deriving the basic equations in fluid mechanics, that is the continuity equation and the momentum equation, we have to know the basic definitions of finite control volume, finite control surface, and infinitesimal fluid element. So, what is finite control volume? A closed volume drawn within a finite region of the flow field is known as a control volume. It is denoted by capital V. Now, what is control surface? A control surface is defined as the closed surface which bounds the volume. Now, to geometrically visualize the control volume and control surface, we select a fixed region inside the flow field, that is the control volume. It has the control surface denoted by capital S. This control surface is fixed in the flow field. The fluid came and passes through this region. While on the other hand, we select a control volume, it is denoted by V, has the control surface S. This control volume moving with the fluid as the fluid goes on the right hand side. Now, it should be understood here that the fluid inside this control volume will always remains the same. Now, what is infinitesimal fluid element? The fluid element is infinitesimal in the same sense as in differential calculus. However, it is large enough to contain a huge number of molecules so that it can be viewed as a continuous medium. Now, to geometrically understand the visualization of the infinitesimal fluid element, here we consider a box which denotes the infinitesimal fluid element which is fixed in this flow field. The fluid came and passes through this infinitesimal fluid element which has the control volume dV, while on the other hand the infinitesimal fluid element having the volume dV moving with the fluid. So there are two scenarios. Number one, the infinitesimal fluid element is fixed in the space and the fluid came and passes through this region. While on the other hand, the infinitesimal fluid element is moving with the fluid. But it should be remembered that the infinitesimal fluid element contains the molecules. These molecules will remain the same throughout the flow. Behavior of the fluid element in the flow field. So when a fluid is flowing, so there are different types of behavior inside the fluid between the molecules. Number one, the translation. Number two, the rotation. So inside the fluid, there are shear stresses due to the viscosity, and also the pressure forces and normal forces are also present inside the fluid flow. So different types of deformations occur inside the fluid as the fluid flow. Number one, the translation, that is the translation occur inside the fluid from one point to another point, while the rotation can also occur inside the fluid. Number third, linear deformation, and number four, angular deformation. In this lecture, just we have studied four different types of deformations that occur inside the fluid flow. Number one, translation. Number two, rotation. Number three, linear deformation, and number four, angular deformations. In this lecture, we are not going to derive the mathematical forms for these types of deformations. I will derive the basic equations for all these four types of deformations in the later lectures. Here, these are just an overview for the students to understand that all these types of deformation may occur inside the fluid flow. Practice problems. Problem number 1 and problem number 2 are provided to the students here. Students are requested to solve these two problems as their homework. If they feel any problem in solving these two problems, they can contact me on my email given at the footnote here. Finally, in references, all the materials in this lecture are provided from the following references.